Okay, so in terms of theory today, it's going to be relatively short. I'd say maybe an hour and a half tops, and then I'll end off with a tutorial, more amplitude modulation, and then we'll stop for today. All right. So what we're going to cover is very important, especially when you're taking a look at synchronized or coherent detection or demodulation. We're going to take a look at two different important topics in communication systems. So one is what's known as the phase lock loop. It's a very important piece of technology. So if you're taking control systems currently, you'll have some appreciation with what I'm going to be talking about today. And then we'll talk about another thing, which is called carrier recovery, which is another method using phase lock loops and a bunch of other techniques to be able to perform synchronized demodulation. So we haven't talked about synchronized demodulations, and this is the point of today's talk. Okay? All right, so in this lecture, we'll talk about two topics that are fundamental in the design of many communication systems. I just talked about this briefly. It's phase lock loop, or which I'll call PLL for short. I'm just going to call it PLL from now on because it's easier to pronounce. And carrier recovery and acquisition. So that's a method to actually determine a synchronized carrier on the receiver end to demodulate your signal. Okay. We're also going to talk about what's known as a super heterodyne receiver, which was an initial attempt or initial electronics system to be able to demodulate amplitude modulated signals, which is actually used during the First and Second World War, which, so if you want to have some historical aspect to it, it was actually used about 50 or 60 years ago. Okay, so this is actually quite a recent technology. Okay, so let's start off with the phase lock loop. What exactly is the phase lock loop? Well, you can think about it as a little tiny electronics control system. Okay, the point of a phase lock loop is you have some carrier, you have some frequency coming in, some cosine coming in, and the objective of the phase lock loop is to match the frequency that the input is giving you. So, for example, if you had some oscillating signal at some frequency, which we'll call omega c, the objective of the phase lock loop is to match the frequency that is coming in, and it gives you a sinusoid that matches that frequency on its way out. So you can think of it as a control system where the input signal or the reference is your carrier wave, and the output will be, so inside here is what is known as a voltage controlled oscillator. So it's basically just a miniature, you can think of that as a carrier, quote unquote, and then the objective is, given an input sinusoid that you put in, the voltage-controlled oscillator will match the frequency of that's coming in and give you an output frequency that matches the input. So think about it in terms like as a reference signal, which is your carrier. The output will be an additional cosine that matches that particular frequency. I also like to point out that there is a 90-degree phase shift for the output. So if you have the input, which is a cosine. Okay, the output is a sinusoid. So there's a 90-degree phase shift, and I'll talk about why this is important later. But it's imperative that you see that the output is a 90-degree phase shift of the input. So it's a control system that tracks a potentially time-varying phase and also the frequency of a carrier component. And this is extremely important because it allows you to perform synchronous or coherent demodulation. It's also used for demodulating FM or PM signals, which we'll talk about later on. But I just want to focus on the aspect of how you can use this for amplitude modulation only. Okay? They're also used quite frequently in digital communication systems, such as if you have what's known as frequency shift keying formatted digital signals, you can certainly use a PLL for that. I'll touch briefly on that later, but it's just a little bit of an added bonus. You don't really need to know that. And also, it's also used for what is known as frequency synthesis. So you have an input signal that's coming in, and then you can actually either increase or decrease the frequency that's coming out. So for example, if you had a frequency that's coming in at 10 hertz, frequency synthesis means that you can actually change what the frequency content will be. So the output may be 15 or 5 hertz, or it actually changes or shifts the frequency for you to a specified amount. Okay, so a PLL has 3 important components inside. So you can think of this as a block diagram with 3 basic components. I'm not going to go into how the electronics work. I'm just going to go exactly into how each component works so you understand basically how it works. And then if you want to take a look at the electronics, I can certainly encourage you to take a look at that on your own time. But I just want to talk about exactly how each of these little blocks works so you have an appreciation of how a PLL works. Okay? So a PLL has 3 functional components. We have what is known as a phase detector, a loop filter, and a voltage-controlled oscillator. And I'll touch base on what those are very soon, or actually the next slide. So a phase detector is basically 3 separate components combined into one. So it consists of what's known as a multiplier, a filter, and an amplitude scaler. Okay? So basically what's happening here is that it takes 2 signals and multiplies them together. It does some sort of filtering, and then it also scales the output to do to facilitate phase detection. And I'll talk about exactly how these three will work to do phase detection for you. But the point of the phase detector is that it determines a difference in phase between the input and the output, and then it adjusts the frequency so that the output that is coming out matches the frequency that is coming in. That's the point of the phase detector. But for now, what we're going to take a look at just for now is we're just going to assume that the phase detector just has a multiplier only, just for now. And then we'll talk about the general case where you actually include the filter and the amplitude scaler. But just consider them as just being a multiplication unit for now. All right? We also have what's known as a loop filter. So a loop filter, the reason why they call it a loop filter is if you actually take a look at this, if you're taking control systems, you can kind of consider this as a closed loop feedback system. So they call this a loop filter because it's a filter that's in a closed feedback loop, right? So it's actually what's known as a narrowband low-pass filter. So it's basically just the low-pass filter that is centered at 0 hertz with a with a bandwidth of whatever tolerance you specify. So it's narrowband means that it looks something like this, right? So minus B to B, and this is an F. So this is what it means by narrowband. Narrowband means that you are centering it's a low-pass filter that's centered at 0 hertz. Okay, and then there's some plus minus B that you want to filter out. Okay, and this is important, and I'll talk about that later. And then what you have then the next component is a voltage-controlled oscillator. So what that does is that it's basically just a sinusoid or some periodic waveform that is oscillating on its own without any input. So if you've taken third-year electronics, you can create a sinusoid or square wave using hysteresis techniques, right? Using positive feedback, you're able to generate a periodic waveform as soon as you turn on the power. As soon as you turn on the power, there's no input, and then it creates a periodic waveform for you. You can think of that as a voltage-controlled oscillator where you can actually control the frequency of your output based on the voltage that comes in. Okay, so that's why it's called a voltage-controlled oscillator, because the output or the frequency can be controlled by the voltage level, which is called V sub E. So this V sub E, you can think of this as an error signal. Okay, this is the output, which I'll talk about soon. Okay, and this is the input that's coming in. Okay, so the frequency of this oscillator, so you can think of an oscillator, it's oscillating at some frequency, some free running frequency. And then depending on what voltage comes into the VCO, the frequency changes. It can either slow down or speed up depending on what the input voltage comes into. That's why it's called voltage control, because the input voltage that comes in will directly affect what frequency you see at the output. Okay, I'm not going to go into what those electronics are, but you can think of it as there's a hysteresis, some sort of hysteresis electronic system, and then you can use some sort of DC bias to actually adjust what the frequency looks like. Okay? All right, so the PLL functions, as I talked about, it's what's known as a closed loop feedback system. So how the PLL works is the following. So you've got so this voltage controlled oscillator, so it's oscillating at some frequency, right, which we'll call F of 0, okay? And then what it does is that if you don't put in anything, if the output is 0, then this voltage controlled oscillator is just going to oscillate at F of 0. And then what this will do is that as soon as you provide an input, then what's going to happen is that this voltage-controlled oscillator is going to try to match the frequency of the input as best as it can, right? So once it tries to match it up, then the output will be pretty much the frequency of the input. Okay, so it locks onto the incoming signal. So what it means is that it'll change the VCO frequency so that it locks onto the input signal. So whatever this will be, whatever omega C is, it'll try to make this output match omega C. Okay, and then once it locks, then any changes that you make, it should be able to track or follow the changes of that frequency. So that, so for example, if you wanted to make the output, let's say 5 hertz, right? As soon as you lock onto it being 5 hertz, any changes you make to the input, the voltage-controlled oscillator should be able to follow those changes. So if you were to change the frequency to, let's say, 6 hertz, then the output should follow it to 6 hertz. Okay. So the reason why you use a PLL is because you're able to not only you're not only able to match the frequency that's coming in, but any changes you make to the input, that output should follow those changes from the input. So you can think of this as a very loose closed-loop control system, where the objective is to follow the reference as best as you can. In this case, the reference is our frequency. We want to follow the input frequency as best as we can. Okay, so that's basically the whole point of a phase lock loop. It tracks the input frequency and it matches whatever input is coming in, that frequency as best as possible. Okay, so basic control system. Okay, so remember what I talked about, the phase detector, for now, we can consider this as just a multiplier. We'll talk about the general case later, but for now, for all intents and purposes, just consider this to be a multiplication of two signals, okay? So the output of the phase detector is basically taking this input, right now, this is an unmodulated carrier. So think of this as, this is just unmodulated. So we're not putting a message signal in, this is just a carrier by itself. So the message signal is not being built in, you're just putting some sinusoid that's coming in. So we have an unmodulated carrier of cos, okay? And remember, the output of this voltage controlled oscillator, notice that there's a phase shift, a 90-degree phase shift. And I'll talk about why you need to do this later, but just take my word for it for now that you have to make sure that the output has to have a 90-degree phase shift comparison to the input. Just take my word for it for now, and I'll talk about why you need that later. So when you multiply these two things together, so we have, okay, so I haven't explained what these terms yet. So we have phi of I and phi of O. What these are is that, you know, due to some noise, or there may be a point where you may not exactly be able to get the right carrier frequency. So for example, if your carrier frequency is 5 hertz, and then, you know, somewhere down the road, there might be some noise that will change it to a bit, maybe to 5.2 or 5.3. So those tolerances are covered by what's phi I of t is. Okay, so it's basically all of the, you know, all of the differences, or all of the things that are introduced that will make it not equal to your desired carrier frequency. So you can think of phi of I and phi of O as, I guess, noise that makes carrier frequency stray from that makes stray from, I guess, original. Sure. Okay, so that's what these are. So there's certain things that they're introduced over time. You know, some random occurrences where the carrier frequency may not equal what you originally intended. So that's what these are modeled after. Okay, so if I were to multiply these two things together, well, you have cos and sine, and then what you can use, you can split this up using product formula, right? So cos of A and sine of B, if I remember my math correctly, it's half of sine A plus B, and then half of sine A minus B. Okay, something like that. I believe that's what it is. So if you were to use this formula and substitute it into here, you'll get this decomposition over here. If I remember, I'm probably wrong here, but basically a product of cos and a sine will give you two sinusoids. Okay. What's important is that we'll see here that this produces two sines of two different frequencies. So we have one which is centered at, the carrier frequency subtract. So, okay, this omega naught here, this is what's known as the free running frequency. So this is the frequency that you set that runs by itself if you don't provide any input. And this here is the carrier frequency. Okay. So we have two components, one at the carrier subtract omega naught, and we have another one at plus. So there's two frequency components. One, you have omega c or fc, which is the center, and then you have one to the left and one to the right, shifted by omega naught. So we have this, that's fine. So why is this important? Well, the reason why this is important is because it'll allow analysis to be easier. So let's consider the easy case, where we don't put in anything into the input. So let's assume for now that we just put in nothing, okay? If we put in nothing, what's gonna happen is that if you take your input, which is 0, and you multiply by some output, which is V naught in this case, when you multiply the two numbers together, you will get 0, which is fine. So because this is 0, this error signal is now equal to 0, okay? So that means that you are not putting anything into the voltage controlled oscillator. So that means that because there's no error, the output oscillation will just be whatever the frequency is designated for this, for this particular piece. So the loop filter output is 0. That means that this here, it continues to operate at whatever frequency you set it at. Okay, so that's totally fine. So you don't put in anything, the output of that VCO will just be whatever frequency that it was set at by you. Okay, and then let's take a look at a couple of harder cases here. So let's say for now that the input is no longer equal to 0. Okay, so it's going to be some non-zero value. So if this input is no longer equal to 0, then what's going to happen is that when you multiply these two things together, right? So what will happen is that you will get a non-zero value. Okay, this means that the error signal is no longer 0. It's going to be some, some positive or negative value is not equal to 0. So that means that because you have some error signal that's coming in, the oscillations or the periodic waveform that is generated by this VCO is going to change depending on what input comes in here. Okay, so so let's assume that it's not equal to 0. Let's say it's actually equal to some, it's actually equal to some cosine wave. Okay, so what'll happen now is that this relationship will hold. We have this relationship here. So what's going to happen is that we have two frequency components centered at, FC minus F0 and FC plus F0. So there's two of them. Okay, so we have some, filter here that's going to, filter out some frequency components at this point. So which one of these is going to make it through the loop filter? Well, if you remember, this is a low-pass filter, right? So one of these is going to make it, and one of these won't. And we'll actually figure out what that'll be. Okay, so if the input is not equal to 0, and what this relationship says is that, let me see here, if F0, let me see, not F0, sorry, it's FC. Actually, no, we can do F0, that's fine. So what this is saying here is that there's two relationships here. So this is saying that if F0 minus FC is greater than some threshold, which we'll call, gamma, okay? And also if, okay? So what this is saying is that there's a tolerance. So if the subtraction of these two is greater than some tolerance, we'll call this tolerance, okay? This is actually what's called the lock range, which we'll talk about later. But basically what's happening here is that the loop filter is designed in such a way where it finds the difference between the free running frequency and the carrier. And if it's larger than a certain amount, then what will happen is that both of those components, right, so both of these components will be set equal to 0. And what that means is that what this implies is if your carrier frequency is too far away in comparison to what the free running frequency is, then it will not track. So what that means is that the output will just be the same free running frequency. So what this means, for example, is let's say your input frequency is, let's say, 10 hertz. And the voltage controlled oscillation, the output is 8 hertz. So the difference, 10 minus 8 is 2. So let's say 2 is a good threshold. But as you start increasing the carrier frequency, and let's say you're going to a kilohertz instead, and the voltage controlled oscillator is still 10 hertz. What's happening here is that your carrier frequency is so far off that it will, this voltage controlled oscillator, this loop here, it will not actually be able to change your carrier frequency down to 8 hertz. It's going to be too far off, and so if it's too far off, then it's not going to do anything. Okay, so here let's see. So if the FC is too far away from the free running frequency, then don't I guess don't change, but VCO is still at f of 0. Okay, so that's what this implies. So there's a range where there's a certain tolerance where if your carrier frequency is within some predefined range, it'll be able to track and give you an output oscillation that'll match the that'll match the two. But then if you make the two values very, very large, then you're not going to be able to track. So then what will happen is that the output will just simply be whatever the frequency you set the voltage control oscillator at. So this is actually what it implies. Okay? All right, so there's the case where we're actually in the predefined range now. So this is, now we're in range. Actually, I'm going to make this black. I don't want to make it orange. Okay, so if we are in range, then what will happen is that, remember, this is a low-pass filter. So if you were to, so the first component here, not actually the second component, if you take the carrier frequency and add it with the free running frequency, that will actually be beyond the bandwidth of the actual. So this is beyond the bandwidth of your loop filter, and that gets eliminated. And what's left is just this single component here instead. And then this gets, this gets maintained, and then you feed it back into the voltage control oscillator. That's the actual voltage that gets put in. Okay, so the loop filter is not equal, the output's not equal to 0, and the output will, the output of here, the error signal will change the frequency of that particular output. So how exactly does this actually work now? So we know that, so this means that it's in range. This means it'll lock, so to speak. So how exactly does it work now if we have your carrier frequency set so that it's within, the predefined range that is within the voltage controlled oscillation frequencies? How does that actually work? Okay, so this is pretty much what it is in a nutshell. Okay, so if the error signal is not equal to 0, then what will happen is that the voltage controlled frequency, so this frequency, the frequency that's generated by the voltage controlled oscillator, it will change in order to reduce the error signal. So what this does is that it will match frequency of input in order to reduce the error signal. Okay, so it will keep reducing, until the frequencies between the two match. Okay, so there are two stages to the phase lock loop. The first stage is what's called the locking stage. So what the locking stage means is that if your carrier frequency is within some predefined threshold, some predefined range between the the free running frequency, that's when that's when it's recognized. And then the next stage is to track. So once you actually track it, that means that the input and the output frequencies will match. So you have to lock first, which means that yes, I'm in this recognized predefined range, and then once I'm in this range, I will then take your input and match the output will match the input carrier's frequency. Okay, so there's locking and there's tracking. Okay, so let's see. All right. Okay, so what we'll do is we'll talk a little bit more about how the electronics work here, not electronics, but the actual system works. So let's assume for the moment that we have an unmodulated carrier. So we don't have any message signal that's coming in. We just have a cosine that is just coming into the input with some error terms that will make it deviate away from the true carrier frequency. Okay, so how you would initially set up, well, it makes sense. What you'd want to do is you want to make the free running frequency equal to the carrier frequency itself. That actually makes the most sense, right? Because you want the output to match whatever input frequency is coming. So this actually does make sense. You want the output to match the input, okay? Now this is what I talked about in terms of the 90-degree phase shift. So I'm going to actually touch base on that now. So the voltage controlled output, that oscillation, that periodic waveform, has to have a 90-degree phase shift in comparison to the input. So why do we have to have a 90-degree phase shift? Well, before I touch on that, if this is the unmodulated carrier, cos, right? If you do a 90-degree phase shift, that means, remember, whenever you do a 90-degree phase shift for a cosine, you get a sinusoid, and that's what's happening here, okay? So the reason why you need a 90-degree phase shift means that it will make the phase the phase detector equal to 0, okay? So that means that it will allow you to make sure that the error signal is 0. That's why you need to have a phase shift of 90 degrees, so that if your carrier frequencies are matched, then there should be no phase shift, or there should be no frequency changes, and the output should finally be equal to 0. And I'll talk about why you need a 90-degree phase shift in order to make the output 0 in a moment. Okay, most PLLs use a square wave as the voltage controlled oscillator. The reason why is because it's a lot easier to actually design. Because if you've ever designed a square wave, if you ever made the electronics for a square wave, especially in ELE 504 or 514 or whatever course you're taking, you can see that it's very easy to create a square wave. You just use hysteresis with positive feedback, and it saturates from plus minus whatever voltages you're coming in. So it's actually very easy to create a square wave. So you use a square wave instead of a sinusoid, and it's actually quite easy to manipulate a square wave, because remember, you can think of a square wave in terms of the Fourier series as a sum of sinusoids, right? So you just filter out the sinusoid that you want. You apply a low-pass filter to a square wave to actually get a sinusoid. So it's usually, you just take a square wave and you put a low-pass filter to actually get a sinusoid in the end. But it's actually a lot easier to use a square wave instead. Okay, so why use a square wave? As I just talked about, it's easier to generate. You can use what's known as hysteresis, right? Hysteresis and positive feedback. Remember, you can use positive feedback and op-amps, right? So remember when you were taught, at least in 404 or 302, that usually negative feedback is good, but sometimes positive feedback, it may not be a good thing, but in this case it is, if you actually want to generate a square wave properly. Okay, so it's easier to generate. And then now we're actually going to talk about the whole shebang here. So there's, the phase detector is a multiply, a filter, and an amplitude scaling. So what this actually does, and I won't prove it here, but the total combination of this is actually, it calculates the area. I won't prove it for you, but if you actually take a look at the electronics, if you actually combine all these things together, what this does is that it finds the area of the product of VI and Vout. So whatever the input's coming in, whatever the output of the voltage controlled oscillator is, if you actually apply all these steps, what this will actually do is that it actually finds the area that is bounded by the product of them, along the as time progresses. Okay, So I won't, this is just the Fourier series representation. I won't prove this for you, but this is just the Fourier series. As I talked about, it's the Fourier series of a square wave. Right? Where, this is, so, okay, so this would be the frequency of the square wave. So between here and here, right? This is defined as, T naught, which is just 1 over F naught, okay? Okay, and you could represent the Fourier series like this. It's very easy to find. So you just you use the Fourier series formula. You go over one period. You find what the d of n coefficients are. You plug it in, and then this is what you get. So you can represent a square wave as a summation of sinusoids. Okay, and if you put a low-pass filter, or you put the right, you apply a right filter on this, you can pretty much filter out all the sinusoids except for the one that's centered at the fundamental frequency, and you can get a sinusoid when you're done there. Okay, so after multiplication and filtering, the phase detector output will only include the fundamental term, which is pretty much what I talked about. Okay. All right, so why the 90-degree phase shift? Okay, so let's actually start slowly here. So let's assume for the moment that we've had some input here. So the input, just for now, we're going to make it so that, so let me see here. Actually, this should be the, we should have some sort of distortion terms here. Okay, so when the input comes in, let's assume that the output, all right, let's assume that they're both matched. Okay, so both of them generate cosine waves. So we have a cos coming in this way, and let's say for now that we have a cos coming in this way. So if both of them are matched exactly, then what will happen here is that when we decide to go through the phase detector, what you're going to do first is you're going to multiply, right? Actually, what this actually should be is this should actually be a square wave. And I don't know why there's a cos here, but you can say this is a square wave at, oopsie, shoot. I hate when that happens. This has very bad palm rejection. Oh, come on. Okay, I'm just going to use my mouse. Okay. There we go. Okay, there we go. There's so many images and all, that's why it's a little slow here. But, okay, so that would go. So actually, I would consider this to be a square wave with fundamental frequency of F naught. In this case, let's assume for now that you want to match them. But that's what we wanted to set it up initially, right? We wanted to make sure that this, the frequency coming in and the voltage controlled frequency, they match up. Okay, that's fine. So, where are we? Okay, so this is the input coming in, all right? And for now, case one is that there's no phase shift. Okay, so this is the first case where there is no phase shift. If there's no phase shift, what will happen is that you'll get a sinusoid that is matched in phase, and then so it's matched in phase with the actual square wave. So remember, the voltage-controlled output will give you a voltage-controlled oscillator gives you a square wave. So what happens when you actually multiply these two things together? Well, if you take a look at the square wave, it just oscillates between -1 and -1 and 1, right? So for any points that are -1, you're going to take those points and simply multiply that with whatever sinusoid you get out. So remember, when you multiply two negatives together, you should get a positive, right? So between here and here, this actually should rectify that so it goes up like that, right? Same thing over here. Same thing over here. So whenever the outputs are both negative, you just rectify them so that they're both positive. Remember, this is square, so it fluctuates between -1 and 1, right? So your sinusoid term or cosinusoid term here, if you take each of those numbers, which are negative, and if you multiply them by -1, you're just flipping it, so that just goes at the top. So what's happening here is you are actually performing a rectification, where any negative values become positive. And that's what's happening here. Okay? So remember what I talked about. So it's it actually, there's some more sophisticated electronics. So you're doing a phase detection, you're doing a filtering, and then you're also doing an amplitude scaling. And then at the very end, it also finds the area as well. So if you were to take a look at this now, and if you actually find the area of this, right? So the area is basically just, it's bounded between the curve and all these, all these outputs which are red, right? So if you actually find what the area is, then, you've actually found, you've actually found the maximum area possible. Okay, so this is what happens when you have two waves that are matched in frequency, but both of them are cosine. Okay, so you want to make the phase detector such that if your two frequencies are matched, you want to be able to make it so that the output is 0. That's what the error signal generates, right? But if both of these are cosines of the same frequencies that are matched, the output of the phase detector actually gives you a non-zero signal. That's not what you want, okay? Now, this actually goes into the reason why we need it to make sure that the output is actually having a 90-degree phase shift, because what will happen is that when you phase shift the square wave, what will happen is that if you actually find the areas, the summation of all those will actually be 0. And I'll actually give you a graphical representation now. Okay, so this is the second case where we want to make sure that there's a phase shift of pi over 2, right? So this is shifted now by 90 degrees. Okay, so if you shift this square wave by 90 degrees, and if you multiply it by the input sign that's going in, this is what's going to happen. Okay, so yeah. Okay, so this is your sine wave coming in, and then this is 90 degree phase shifted, 90 degrees shifted. Okay, so what will happen now is we can actually break this up into two regions. Okay, so the first region, right, we have a negative with a positive, so that remains. Okay, then what will happen is that between here and here, right, between here and here you get a negative and negative, so that becomes positive. So the output will look like this, so 1 and then 2, like that. And then this stays the same, this stays the same, and then what's happening here is that this gets rectified, so you have something like that, right? And then it keeps going, it keeps going. So the ramifications of this, what's happening here, actually no, I'm sorry, that's not what happens. So you have a negative and the positive, that still remains. So any points where the square wave is negative, you just rectify it. So the output goes like this, right? Output goes like this, and so on and so forth. So when you actually work this out, you see that we get this now, okay? So this is what the red wave looks like. Okay, and then when you actually add up all the areas, what's going to happen is that you'll have this area and this area, they cancel, right? This area and this area, they cancel, and this keeps going. This keeps going, okay? And this is the reason why you need a phase shift of minus pi over 2. It's because you want to make it so that when the two frequencies, when the two inputs that are coming in, when they match your frequency, you want to make it so that the output, the error signal is 0. And this is what is happening here. So when you phase shift by pi over 2, and then when you find the areas that are bounded, all these areas cancel, and then you finally get the output to be 0. And that's the reason why you need a 90-degree phase shift. It's because you want to make it so that the carrier frequency that's coming in and the voltage-controlled oscillator frequency, when they match, you want to make sure that that error signal is 0, and that's why you have to make sure that there's a 90-degree phase shift. So if there isn't, then what will happen is that it produces a non-error signal, a non-zero error signal, and that's not what you want. Okay, so that's the reason why you need a 90-degree phase shift. It's to make sure that the phase detector output will make sure that there is actually no error signal when you actually match the frequencies. Okay? Okay, so this is the next case where we actually do, let's say we actually do a 180-degree phase shift instead. Okay, so instead of it, so let's say for the moment that the cosine, instead of it being positive, it's negative instead. Okay, so we can follow through the same logic, right? So if the square wave is rectified, so that instead of plus, actually, remember, this should be a square wave, sorry. I don't know why there's a cos there, but just flip the sign. So what will happen is that you're doing what's known as a negative rectification, okay? So anytime the square wave goes negative, right, you're taking your positive amplitude for your input and multiplying it by -1. So what's happening here is that all the values just get pushed below the negative. And if you actually find the area, you'll see that it actually produces, I guess, what you call a negative area, and that's actually the smallest you can find. Okay? So that's the reason why I need a pi over 2. So even if you do a 180-degree phase shift, the total error will, the total area will give you some number. It'll just be the negative representation of a positive side, but still, the error signal is not equal to 0, and that's why you need a 90-degree phase shift. Okay? All right, so here's some terminology that I'll talk about here, and then I'll give you a couple of applications for PLL, and then we'll take a break. Okay? So when you're taking a look at phase lock loop, there are 3 parameters that you have to be concerned with. Okay? The first one we're already acquainted with. This is what's known as the free running frequency or the center frequency. This is basically the frequency that you set by yourself, where if you don't put in any input signal into the phase lock loop, this is the frequency, this is the output that will give you. So this will be the output periodic waveform, or the waveform that will be given to you if you put in no input. Okay? So this is the frequency at which the voltage-controlled oscillator operates when you have no error. So you can actually set this for yourself. So usually you want to make sure that the voltage controlled oscillator is set to be whatever the carrier frequency is that's coming in. All right, so we usually want to do that. So sorry. Yeah, usually F0, FC. Okay, we usually want that to happen. That makes sense. Okay. Then you have what's known as the lock, tracking, or hold-in range. Basically, what's happening here is that you have to make your carrier frequency within the vicinity of your free running frequency. So it has to be within some tolerance of the free running frequency to recognize it and say, okay, I have to start tracking the signal and I have to actually start making it so that the output frequency matches the input. So that's what the lock, tracking, or hold-in range is. So once you finally lock onto your signal, then there's another variable which is called the capture range. So once you lock onto your signal, this is the tolerance where, as you start varying your carrier frequency, the output will match the frequency that you tune in for the input. And then if you exceed this range, then what will happen is that the output frequency will simply fall back to what the free running frequency would be. Okay? So this is the maximum initial frequency difference between F0 and FC, so which can acquire the lock. Okay, so this is all like terminology and all. And it would be nice to actually show you a couple of graphs. Okay, so here's the first graph I'll show. So how do you actually measure the the ranges? How do you measure the lock range and the capture range? Well, let's say here that we have a function generator that we've attached to this phase lock loop, and we want to adjust. So this is the carrier frequency. So what we want to do is we want to turn the knob so that we change with the carrier frequency, starting from very low to very high. Okay, so this would be your carrier frequency. Okay, so if you were to adjust this so that you're changing the input frequency so that it becomes larger, this is what is visualized. Okay, so F0 here, this is your free running frequency. Okay, and what happens here is that as you start increasing your carrier frequency, it makes sense that the range to lock the frequency it decreases, right? It makes sense because as you start increasing the carrier frequency, you have very little room left in the voltage controlled oscillator to be able to lock onto the signal. So remember, as you're going farther away from the as you're going farther away from the voltage controlled oscillation frequency, the less likely it's going to be for you to actually say, hey, I need to track this input signal, and then you start actually tracking it. So that's what's happening here. So as you start increasing it, you notice that the capture range gets smaller, but then consequently, as soon as you actually no, sorry, lock range. Actually, let me see here, lock range, capture range. That's actually flipped. I don't know why that is, but yeah, that actually should be flipped. But anyway, so as you start, increasing your frequency, it gets to a point where there's very little chance for you to lock on, but then once you actually lock on, then there's actually going to be some tolerance where if you were to change your frequency dramatically, then the voltage controlled oscillator should be able to track whatever input frequency is coming in. Okay, so once you actually lock onto it, then as you start varying the frequency, it should have a little bit more tolerance. And then this is what happens when you actually decrease. So when you decrease, well, that makes sense. It makes sense where if you decrease the voltage control oscillation, you get to a point where you're going to start matching. You're going to start slowly going towards what the free running frequency would be. So there's going to be more of a chance to actually lock onto your actual frequencies, right? To lock onto the actual input. And then but then coincidentally, the capture range will be slightly decreased. So if you actually put these two things together, this is what you see here. So this is right at the point, right here, where, so remember, so the horizontal, the vertical axis here, this is the error signal, right? So this is the error signal, and then this would be the frequency that goes in. So when you match the frequencies, when you match the voltage control oscillator and the carrier, there should be no error signal, which actually makes sense, okay? As you start increasing the frequency, what's going to happen here is that the error signal is going to increase, which does make sense, right? So as you start increasing the frequencies, the error is going to keep increasing. It's going to keep increasing up until the point where we get out of the capture range. And when we get out of the capture range, we don't, we don't lock it anymore. And then we're gone to the point where we don't track it anymore. And then the output frequency is just simply equal to the voltage controlled oscillation, and then that's when the error signal is 0. And then the same thing when you go on the left side too. So as you start decreasing the frequency, you'll get to the point where the error signal starts decreasing, becomes negative, up to the point where you exceed the capture range, and then it just falls back to whatever the voltage controlled oscillator would be. Okay, so here's a couple of applications, then we'll take a break. The first application is taking a look at coherent demodulation for AM signals. So remember, if you have an AM signal, which is what's known as overmodulated, or you get a point where when you take the carrier amplitude and if you add it with your message, if it goes below the horizontal axis, then you can't use an envelope detector anymore. So you have to use coherent modulation techniques. And you can use the PLL to demodulate AM signals quite successfully. Okay, so the process to do that is quite simple. Okay, so what you do here is you have your amplitude modulated signal coming in, okay, and then what's going to happen is that you're going to take this signal and then you're going to put it through the PLL, and the output of this here, right, what this will do is that it'll generate, so this actually generates a cosine wave for you, so to speak. Okay, so the output, so when you put this through here, this voltage controlled output, this outputs it's a sine wave because you have a 90-degree phase shift, right? So when you put your amplitude modulated signal through here, remember the output is just a sine wave. In this case, you can just put a filter here if you wish. So if you put a filter here, because usually it's a square wave, right? If you put a filter in the output, you will get a sine wave, okay? And then remember, this is 90-degree phase shift with respect to this, and then if you do an additional phase shift, you'll get a cosine wave, and then what's happening here is that this here is coherent demodulation. It's actually quite nice because what you're doing is that you are trying to find the carrier signal that is embedded inside the AM signal, and then you're going to use that signal that you extract out from the AM signal. You multiply the two signals together, and then that performs coherent demodulation, right? So you're actually using a copy of itself to extract out what the original carrier was. So then when the amplitude modulating signal comes in, you'll get it to be matched with the carrier frequency that's coming. So you have a cosine wave that matches the carrier frequency of the AM signal. So when you multiply them together, you get a synchronized signal. Then you apply a low-pass filter and then a DC block, and then you can finally get your original signal. So it's nice here because you are basically using your AM signal, and the output here is a sinusoid or cosine that matches the frequencies exactly between the two. And then when you multiply them together, they're synchronized, and then you finally get a demodulated output that is using coherent detection. Okay, this is just another application here. You can actually use this for frequency demodulation. And I'll talk about this in a little bit here. But basically what you have is that you basically take your FM signal and then just put it through a phase lock loop. And the output by itself is just the message signal by itself. But this is, we'll talk about this later when we talk about frequency modulation, the next part of the course. But you'll see later, especially in your labs, that if you actually just take a frequency modulated signal and put it through a PLL by itself outright, the error signal that you get is actually the message signal, which is actually, it's a little messed up, but we'll actually talk about why this is later on in the course. Okay, so this is, you actually take a look at the error signal. And whatever the error signal is, right, that will actually be the message, which is actually pretty cool. Okay. So this is another application which is what's known as sweep acquisition. So what that means specifically is that, let's see here. So, I see, sweep acquisition. So how this works is that if you have some sort of, I'll explain this later in the next class or so. But what sweep acquisition does is that it actually sweeps the range of frequencies. So let's say you actually don't know what the carrier frequency was. So what sweep acquisition does is that it will actually figure out, it'll sweep from very low to very high, it'll sweep all frequencies to figure out what the actual true carrier frequency is, and then it'll use that to actually demodulate your signal. So sweep acquisition, what it does is that if f of c is unknown. Okay, so the reason why you have a ramp is because you're actually varying the voltage controlled output based on the ramp. So when you start from very low to very high, you're actually changing the frequency of the voltage controlled oscillator as you start increasing the ramps. Remember, a ramp is basically starting from 0 and then it goes in a linear fashion, right? So this ramp, what it does is that the purpose is to generate all these different kinds of frequencies that the voltage controlled oscillator will output, and then you use this logic here to figure out exactly what the carrier frequency is. So once you actually figure out what the carrier frequency is, you lock onto that carrier frequency, and then you use that to demodulate your signal. So this is actually nice, where if you're doing it where if you actually don't know what the carrier frequency is of your FM signal, this logic here, which I'll explain in a couple classes from now, will actually figure out what your carrier frequency is and then successfully demodulate your signal. That's why it's called sweep acquisition, because you're sweeping from very low frequencies to very high frequencies to identify what the actual carrier frequency is to successfully demodulate your signal. Okay? And then here's the last application. This is what I was talking about, where if you want to generate a cosine or a sinusoid of a different frequency, so if your input frequency is, let's say, 5 hertz, then frequency synthesis will allow you to generate a frequency of a different, it'll allow you to generate a wave of a different frequency. Okay? So the electronics here are such that if you specify, some gains, which are M or N, for example, the output will actually be the ratio of the two multiplied by whatever message frequency that is coming in. Okay, and this is the last application here. So this is what is known as frequency shift keying. So this is used in digital communication systems where it fluctuates between two different frequencies. So if you wanted to transmit 0, it has a cosine of some low frequency. If you want to transmit 1, the output will be a higher frequency. So what you can do here is you can actually use 2 PLLs that are tuned for each of the frequencies that it's detecting for. And then what you can do here is you can actually take a look at the errors, see which one has the lower error, and then you would choose whatever has the lower error to be the recognized symbol. So if you had if you put your signal through here, then if you see that the first one has a lower error compared to the second one, then you output a 0, and then if it's the other way around, then you output a 1. So this is a very basic way to demodulate, which is what's known as frequency shift keying, which changes the frequency of your carrier depending on what the binary bit would be. So 0 is a lower frequency and 1 is a higher frequency. Okay, so we'll take a break here. Come back, we'll talk about carrier acquisition. Should take about maybe half an hour or so. Then I'll end today's talk with a tutorial, and hopefully we'll get out of here probably by 8 or 8:15, the latest. Okay?